In section 4.4, we're going to look at an approach which is called undetermined coefficients, the superposition approach. The goal of this section is to solve a non-homogeneous linear differential equation of the form an y sub n plus a sub n minus 1 y sub n minus 1 plus all the way down to a sub 0 times the original function y is equal to g of x. In order to solve such a linear differential equation, we need to do two things. The first thing we're going to do is find the complementary function y sub c. And if you recall from section 4.1, y sub c is found by solving the associated homogeneous differential equation, where instead of having g of x on the right-hand side, you first solve it set equal to 0. And that was the kind of thing we did back in section 4.3. Once we've successfully accomplished that, then we're going to work on the thing which is going to be new to this section, and that's to find a second solution, which is referred to as any particular solution y sub p of the non-homogeneous equation from above. The general solution then will be just the sum of the complementary solution along with the particular solution. Again, y sub c, we know how to solve this from section 4.3. And the y sub p will be the thing that's going to be new to us this time around. There will be two different methods for solving for y sub p. In 4.4, we're going to use what's called the superposition approach, or undetermined coefficients. And then when we turn our attention to section 4.5, we'll take a slightly different approach, which is referred to as the annihilator approach. Okay. So again, a couple things here. The coefficients that we're working with, these are going to be constants. So the coefficients that are in front of these derivatives and the original function, these are all constant coefficients. And then the next thing is that g of x is going to be any constant k. It could be a polynomial function, an exponential function, a sine or a cosine, or a finite sums and products of these functions. Okay. So we're going to kind of restrict our attention a little bit for a particular type of g of x in this section. And pretty much we're going to restrict ourselves to the classical types of functions we're used to working with, mainly from, like, let's say, pre-calculus. So g of x itself could be a polynomial. This includes a polynomial of degree 0, which would be like your constant functions. It could be an exponential function, sines or cosines, or any product of those types of functions, or sums of those types of functions. Okay. So for example, these would be like types of possibilities we could have for like g of x. Any one of these functions listed here would be a potential for our g of x on the right-hand side of this differential equation. Okay, it could be a constant function, could be a polynomial, it could be a polynomial with a exponential term added to it, could be a trig function, or a trig function cosine of 2x, times the polynomial negative 5x, or something like this where we have x e to the x sine x. So this is the product of a polynomial, the polynomial x, e to the x, as well as sine of x, and then we also are adding to it the product of a polynomial with e to some power. So to make a long story short, the functions we're going to look at on the right-hand side when we're trying to solve for the particular solution, they're going to be one of the following forms. It would be p of x could be either a polynomial, or a polynomial times e to some power, or a polynomial times e times sine, or a polynomial times e times a cosine. Okay. The method of undetermined coefficients, so what we're going to talk about in this section, would not apply to these types of g of x functions. ln of x, 1 over x, tangent of x, and sine inverse of x. We could still find the complementary solution, the y sub c, using the things we talked about in the last section, but the method of undetermined coefficients would not work for functions of this type. Okay. The set of functions that consist of constants, polynomials, exponential sines, and cosines has the remarkable property that the derivatives of their sums and products are again sums and products of constants, polynomials, exponentials, sines, and cosines. Meaning that if we remember kind of like our rules from Calculus 1, and also Calculus 2 as well, that, you know, when we take the derivatives of these types of functions, the derivatives also end up being of more or less the same type. And so if we're trying to find a particular solution to satisfy a differential equation, it's kind of safe to assume that the original function itself, the y sub p that we're looking for, may very well be of a form that's similar to the ending function we get, which is the g of x function on the right-hand side. Let's look at an example of one of these together. Let's take a look at example 1. In example 1, we want to solve the differential equation y double prime plus 4y prime minus 2y equals to 2x squared minus 3x plus 6. Okay. So let's go ahead and do this together. The first step, step 1, is we want to find the complementary solution. We're looking for y sub c. Y sub c, if you remember, this is found by solving the associated homogeneous differential equation y double prime plus 4y prime minus 2y equals to 0. From this we can solve for the values of m. So the corresponding auxiliary equation would be m squared plus 4m minus 2 equals to 0. This is what we did back in section 4.3. It would be nice if this factors, but it doesn't. But we can go ahead and use the quadratic formula. A would be equal to 1, B is equal to 4, and C is equal to negative 2. So we have negative B plus or minus the square root of B squared minus 4 times A times C, all divided by 2 times A. That is m equals negative 4 plus or minus the square root of, we're going to have 16 minus a minus 8 will be 16 plus 8, which is 24 over 2. This is negative 4 plus 24 is the square root of 4 times the square root of 6. So that's going to be 2 radical 6 over 2. And we get that m is equal to, divide out by the common factor of 2, we get negative 2 plus or minus the square root of 6. So we get two values, two distinct real values for m. So we recall that that means, in this case, that the complementary solution will be of the form c1 e to the m1x plus c2 e to the m2x. So we have y sub c equals c1 e raised to the negative 2 plus the square root of 6 times x, and then plus c2 e raised to the negative 2 minus the square root of x plus negative 2 minus the square root of x times 6. So this is our complementary solution. The next thing we want to do is find y sub p. The way that we're going to find y sub p is by looking at the following function. And I'll post some guidelines in D2L, some notes on some suggestions on what to suggest for y sub p. So what we're going to do for y sub p is we're going to make an educated guess based upon the form of g of x. Well, if we look at g of x is 2x squared minus 3x plus 6. That's a polynomial of degree 2. So it very well may be the case that y sub p, our particular solution, could also perhaps be a polynomial of degree 2. So let's assume that y of p has the form ax squared plus bx, and I'm not sure why I put 6 there. How about plus c? And let's see if we can find coefficients a, b, and c such that this y sub p would be a solution to our non-homogeneous differential equation. And this is what we mean by like the undetermined coefficients. We're trying to find a, b, and c such that y of p will be a solution. In order to do that, we need to plug y sub p into this differential equation. So we're also going to need the derivative. We need y sub p prime. The first derivative would be 2ax plus b, and then the second derivative would simply be 2a. Okay. Let's plug these into the differential equation. So it's y double prime, that's 2a plus 4 times y prime. Well, y prime is 2ax plus b minus 2 times y. Y is ax squared plus bx plus c. And this is supposed to be equal to 2x squared minus 3x plus 6. So we have this equation. We need to solve it for a, b, and c. First thing we're going to do is let's eliminate all of the parentheses by distributing. So we have 2a plus, this will be an 8ax plus 4b minus 2ax squared minus 2bx minus 2c is equal to 2x squared minus 3x plus 6. And now what we're going to do is we're going to essentially combine like terms on this left-hand side, which essentially just kind of amounts to factoring out common terms for the variable x. So first of all, I have a negative 2ax squared. That's my only x squared term. Now, which terms have an x in it? Well, this one here, as well as this one here. Their coefficients are 8a minus 2b. So if you think of taking those two, grouping them together, and then factoring out the x, what you would have would be an 8a minus 2b. And then whatever's left over, that's going to constitute our constant term. We have 2a plus 4b minus 2c. So 2a plus 4b minus 2c. And this whole thing is equal to 2x squared minus 3x plus 6. And just gonna kind of come over here and clear some space. To proceed from here, what we want to do is think of this equation, think of this as not just an equality of two algebraic expressions. Oops, my apologies. Let's bring back our negative 2a here. But think of this as an equality on two polynomials. In order for two polynomials to be equal, they have to have exactly the same degree, and they have to have the same coefficients. So what we're going to do here is we're going to equate the coefficients. So for example, the coefficient of the x squared term here, which is negative 2a, would have to match up with the coefficient of the x squared term on the right-hand side. And so that will tell us that negative 2a must be equal to 2. Similarly, we need the coefficients of the x terms to match up, meaning that this coefficient here has to match this negative 3 coefficient. So we need 8a minus 2b to be equal to negative 3. And then in addition, the constant coefficients must match up. So we need 2a plus 4b minus 2c must be equal to positive 6. So 2a plus 4b minus 2c has to be equal to positive 6. And what we have here, for those of you that have had linear algebra in the past, this is a system of 3 equations in 3 unknowns. There's a lot of different techniques and things you can use to solve this. Things such as substitution method, elimination method, Gauss-Jordan type things. But there's ways to solve this, right? You can even transform this into matrices if you know how to apply matrix inverses, for example. But luckily for us, this is a pretty easy system, because if we go to the first equation, if negative 2a equals to 2, we can solve for a by dividing both sides by negative 2, and we get that a would be equal to negative 1. And now that I know that a is negative 1, I can solve it, plug it into the second equation to solve for the value of b. 8 times negative 1 minus 2b would be equal to negative 3. That means that negative 8 minus 2b equals negative 3. we would add 8 to both sides. Negative 2b would be equal to a positive 5. So b would be negative 5 halves. And now that we know a and b, we can plug those both into the last part in order to solve for c. Okay. So 2 times negative 1 plus 4 times negative 5 halves minus 2c should be equal to 6. So negative 2, 4 times negative 5 halves, that'll be negative 10, minus 2c equals to 6. That is negative 12 minus 2c equals to 6. Add 12 to both sides. Negative 2c equals to 18. Divide by negative 2, and we would find that c is going to be equal to negative 9. So we know a, we know b, and we know c. Therefore, going back, the particular solution to this differential equation is the following. So y particular, it's a times x squared, where we know a is negative 1, so it's negative x squared, plus b is negative 5 halves, so it's going to be minus, whoops, my apologies, come on back, there we go, negative 5 halves x, and then plus c, which is negative 9. So this gives us our particular solution to the differential equation. So we found the complementary solution by solving the homogeneous differential equation. We found the particular solution by looking at the form of g of x, assuming that the original function y was of a form compatible or similar to g of x. We then plugged our guess, if you will, or our recommendation based upon our knowledge of derivatives into the differential equation. We solved for the undetermined coefficients. We found a, b, and c. That gave us the particular solution. And now we're ready to state our final case. So the general solution to this differential equation, we'll call it y, it's simply the sum of the complementary solution plus the particular solution. So our solution is y equals, we have c1 e to the negative 2 plus radical 6x plus c2 e to the negative 2 minus the square root of 6x minus x squared minus 5 halves x minus 9. So that is our general solution to the differential equation. Again, we're not going to check this one. If you wanted to, it's a good exercise. Go ahead and take the first derivative, the second derivative, plug it in. But this is our general solution to that differential equation.